Hello and welcome everyone to this month's webinar. I'll go ahead and get started with just a brief introduction to Kenexis if you're not familiar with us. We are a process safety consulting engineering company. We provide a full complement of engineering services, software, and training. To learn more about our products and services, please visit Kenexis.com for more information, or if you like, you can reach out to me directly at chris.phillips@kenexis.com. Chris with a K, K-R-I-S. Our goal is to do one of these webinars per month, so please consider subscribing to our newsletter on the website. That way you'll be up to date on the timing and subject matter of our future webinars. We also put some other important information in our newsletters. We are very conscious about our messaging, so we won't overload you with a lot of repetitive information. And you can unsubscribe to the newsletter if you ever feel the need to do so, but we think you'll find it rather useful. We also post our upcoming webinars and other information on our LinkedIn page, so please consider following Kenexis on LinkedIn as well. And with that, I'll go ahead and turn it over to today's presenter, President of Kenexis, Ed Marzell. It's all yours, Ed.
All right, thanks. In today's presentation, I'm going to share my screen. And it's an interesting presentation. It's not a normal kind of training class thing. It's basically, I'm going to be grabbing information from a bunch of different places to talk about. The topic is the SIL equations. So the PFD equations, the spurious trip rate equations. Everybody knows that the standard IEC 61511 requires us to perform calculations to verify that our safety instrumented functions achieve their performance targets. Well, those equations, where did they come from? Why are there so many terms? What do those terms represent? There's a lot of, I don't want to say a misunderstanding, but maybe a lack of knowledge on the purpose of the terms, when they're applied and why they're applied. So like I said, I'm going to be hitting a couple of PDF files. I'm going to be hitting a couple of different PowerPoint decks to kind of go over this information, but let's begin at the beginning. Most of you, when you're doing SIL verification, you're going to use some sort of tool to do that SIL verification, like Kenexis Integrated Safety Suite, which I have up on the screen here. Let me log in real quick. And once I go into Kenexis Integrated Safety Suite, I'm going to go to the General Oil and Gas Operating Company, which is a fictitious company we created to do demos and training classes. When I go in and you look at a typical SIF, so let me pull up the SIF list. So if I bring up the IPF list for this study and bring up a typical safety function, so high pressure separator, high pressure closes the shutoff valve, we need to be able to achieve the target. So our LOPA said we needed a risk reduction factor of 120. We achieved a risk reduction factor of 206 with a PFD of 4.84 E-3. Now, as you know, typically, safety instrumented functions are built out of three pieces. You have a piece for the sensor, a piece for the logic solver, and a piece for the final elements. And you're going to add their probabilities of failure together because they are logically related as an OR. So for OR, we use probability addition, meaning that the probability of failure of a SIF will occur if we have a failure in the sensor subsystem, or a failure in the logic solver subsystem, or a failure in the final element subsystem. So you're essentially adding. It's a little bit more complicated than that, but for very small numbers, you're effectively just adding them together. So the total PFD is going to be the PFD of the sensor subsystem, which you see is 1.06 E-3. I'm sorry, 1.06 E-3 is the final element subsystem. Logic solver subsystem, 1.39 E-4 sensor subsystem, 3.63 E-3. You add those together, and that's where this 4.84 E-3 came from. So again, with all of these fancy tools for performing SIL verification calculations. At the end of the day, there's a fairly, I don't want to call it simple, but there's a well-defined process for how the calculations are being performed. Okay, now if we drill down a little bit deeper, so I'm going to bring up the worksheet for the sensor itself, you'll see that that PFD of 3.64 E-3 that is related to the sensor subsystem is actually built of a lot of different components. So you'll see 3.64 E-3 is the sum of 2.34 E-3, 1.29 E-3. There's a 0 here, a 0 here, and then 9.32 E-6. You add all those together. So when you're calculating the PFD, you're actually adding together multiple terms. And those multiple terms, sometimes you use them, sometimes you don't use them, depending on how you, the end user, configure your system. And I'm going to go and I'm going to explain what all of these terms are and where they came from. And it's also similar for the spurious trip rate. So there is, in this case, we added 3 terms together to calculate the spurious trip rate, which totals up to 4.55 E-8. So what are these terms? Where did they come from? Well, let's go back, and I'm going to cancel out of here, and I'm going to go back into the Wayback Machine. And I'm going to show you a technical report from ISA. This technical report was released in 2002, which was almost a decade after I joined the committee. I joined the committee in 1994. But you'll see that the first original 1-out-of-1 equation only contained effectively 1 term. Ignore this term at the end, which is the probability of failure associated with systematic failures. The standard, and this could actually be the topic of an entirely different seminar, why you don't include human failures in your PFD calculations. The standard specifically says random hardware failures are what you're calculating, and there's a very good reason why you would do that, but that's another 20-minute discussion, which maybe, Chris, you might want to note that down, that we could talk about why you don't include systematic failures in your PFD calculations as another webinar we can get into. But effectively, you only have this one term, lambda du times test interval over 2. And this actually might be correct for your system. What this assumes is that the failures of your safety system, if you can detect a failure with diagnostics, then you're configuring your shutdown system to automatically shut down. It's also assuming that your proof testing is 100% perfect, which it probably isn't. I'll get into that. It's assuming that you're never bypassing the system while the plant's online and running to perform a test. Well, common cause doesn't come into play until we have redundancy, and a 1-out-of-1 voting arrangement does not have redundancy. So this is kind of the starting point from 2002 from the ISA technical report, TR 84.00.02. Let me get my magic pencil out and start drawing on the screen. So that's the old version of this technical report. There's been, I think the most recent version of this is 2015, so there are a lot more terms. So how did we get from here to where we are today? And well, actually, let's jump back and ask ourselves, well, where are we today in terms of these calculations? So let me get out of the web browser, and I'm going to go and I'm going to show you the ISA EC50 training class. So this is SIS, a lifecycle approach. I highly recommend this class. I highly recommend ISA's certifications, really top notch, best in the world. But if you look at slide 109, and I have all of this information because I primarily teach the class. Now that Paul Gruen is retired, I'm technically the owner of the class. But if you look at slide 109 here in the ISA training class, you're going to see 4 terms and kind of a placeholder for term number 5, which is common cause, which doesn't show up in the 1-out-of-1 voting configuration. You'll see that there are 4 terms that you need to consider. And this guy in the middle here, that's the only one that was in that 2002 version of the technical report. This is what we call the DU term, the dangerous undetected term. And I'll explore these in a little bit more detail in just a few minutes. But first, I'm just going to list out what they are. The other terms that have been added include this term here, which is the dangerous detected portion, which I'll call the DD term. The reason that this term sometimes needs to be evaluated is because if you have diagnostics and you can detect that a failure has occurred, you can shut down, and that will mean if you shut down, your plant is never unavailable because of a dangerous detected failure, because as soon as you know that it's present, you shut down. So there's no time you're unavailable because of a dangerous detected failure. But you can also make the choice when you detect a failure. So let's say I have an SIS level measurement and a BPCS level measurement, and I have a diagnostics that's a deviation alarm between those 2 level measurements. If that deviation alarm goes up and says, hey, one of these 2 transmitters is in the failed state, and it very well could be the level transmitter in the SIS that's in the failed state, are you going to shut down? Most plants are not going to shut down on that deviation alarm. So in that case, we might have had a dangerous failure, that's the first D, and that failure was detected by the diagnostics or our deviation alarm. But instead of shutting down the plant, I'm going to continue to operate even though that level transmitter that is necessary for the shutdown is now unavailable. So that's the DD term. If you choose not to shut down, even though you detected a failure, and you just continue to operate while that device is repaired, now you need to evaluate this term. The original 2002 ISA report assumed when you detected a failure, you're always going to shut down, but that's not always the case, so we had to add the term. Now, we have the never detected portion. So we are assuming when we look at our proof testing of SIS, or back in the 2002 version of the report, we assumed that if we test an SIS component and it passes the test, it's gonna work. But in reality, that's not necessarily always true. It depends on how good your tests are. So I'll come back and give you some examples of some poorly executed tests that are not going to give you 100% diagnostic coverage. And even after the test is performed, this failure mode can still be present. And that's why there's a portion of the failure rate that you will never detect, not by your automatic diagnostics, not by your manual proof tests. And this additional term, which we call the DN term, dangerous never detected failures, is something that you generally are going to need to evaluate for every instrument unless you are 100% certain that the function testing is going to detect 100% of the failures, which is possible maybe for something like a motor starter. It's hard for that motor starter to drop out and say, well, it didn't really drop out. But for a lot of field instruments that are processed wet, getting 100% diagnostic coverage is a tough thing to do. The next term, which has many names, I'm going to call it the online testing term. If you perform online testing, and more we are doing online testing, While you're doing your testing, you'll generally put your safety function in bypass. While the safety function is in bypass, it is unavailable to perform its safety instrumented function. As a result, that unavailability needs to be added to your overall probability of failure on demand. So the OT online testing term is becoming more and more relevant because turnarounds are expensive. And if I can shave a day off of my plant's turnaround by doing my SIS testing, at least of my sensors, while the plant is online and running, I save myself many millions of dollars. But if you're in bypass to execute that test, you need to take the unavailability while you're performing that test and include it in the probability of failure on demand. That is the online testing term. So, and then you're also going to have your common cause failures or your CC failures if you have redundancy. 1 out of 1 does not have redundancy, but 1 out of 2, 2 out of 2, 2 out of 3 do have redundancy, and you'll want to add those common cause terms. So if I go back, discard my ink annotations. If I go back to Vertigo now and look at this worksheet on an instrument by instrument basis, you'll see that all of the terms are going to show up. So this first term that you see in Vertigo is that DU term. So kind of flipping back and forth, it is this DU term here. So that DU term is the one that's getting calculated in that slot there. Then you have a common cause term, which requires you to know what the beta factor is. And if you don't know what the beta factor is, you can use the IEC 61508 beta factor estimator that's built in here to estimate what it is. 5% is a very common number, generally applicable to most of your plant instances. Okay, so that beta factor term gets calculated, and you'll notice it's not just calculated for the PFD, it's also going to be calculated for the spurious trip rate if you have redundancy. Okay, the next term is this term that we kind of have this checkbox to say click on detected failure. So in Vertigo, you can turn these terms on and off. So if I didn't want to calculate common cause, I could uncheck that button and it won't calculate it anymore. But I'm going to hit this check button. I'm going to put in a beta factor of 5%, and it's going to calculate that term. The next term is trip on detected failure. So now what you're doing is you're explaining what the behavior is if you detect a dangerous failure. So let's go back to that level transmitter. So let's say that level transmitter is running at 12 milliamps, 50% level. And then one scan later, the analog input signal goes from 12 milliamps to 0. Okay, a functioning transmitter will never go to 0. If it's 0, it will go to 4. So because you went from 12 milliamps one scan to 0 the next scan, you know that the transmitter is not voting to trip. It's broken. It's busted. So what do you do when you detect that that failure has occurred? Well, right now, what you're seeing on the screen, the checkbox says trip on detected failure. When you trip on the detected failure, your safety function is never unavailable while the plant is running because you shut the plant down. But because you shut the plant down, you generated a spurious trip. So what we did was took that the lambda S, and I'll come back to the ISA training class and show you kind of the failure rate split breakdown, but that lambda S gets moved over, and I love the way that Vertigo does this. You actually have a ledger. There's a PFD ledger and a spurious trip rate ledger. So we're gonna, if we trip on a detected failure, we're gonna take that the lambda S and we're going to shove it over to the spurious trip rate side of the ledger instead of the PFD side of the ledger, because we program the system to take this dangerous detected failure and make it a safe failure by causing the plant to shut down when a hazard is not actually present, which is why when you check on trip undetected failure, it's going to increase the spurious trip rate. But if I uncheck it, it's no longer considering that lambda S to be a spurious trip rate, or lambda SD, the detected, or I'm sorry, have I been saying lambda SD? I'm so sorry. It's lambda DD. It's the DD term, dangerous detected failure. I apologize for that. So everywhere you just heard me say lambda S, I meant to say lambda DD. Okay. Now we're not calculating the PFD yet because we need information on, and I'll go back into the equations. We need information on how long does it take to detect that this failure has occurred. So I'm going to just throw a 0 in because, and the dangerous detected term is going to rely on this mean time to repair, and it's also going to rely on the diagnostic test interval. When you add those two things together, that is the time period that you're going to be unavailable for. More on that when we go into the equations. But the reason I put 0 in is the diagnostic test interval of a PLC and a pressure or a level transmitter is, one scan. So let's call it 300 milliseconds. Well, if I add 300 milliseconds to 72 hours, I pretty much still have 72 hours. So for real high turnaround diagnostics, you're always going to put a 0 here. The only time you wouldn't put a 0 is a very slow diagnostic, like a partial stroke test that might only occur once a week or once a month or once a quarter. Then that test interval becomes relevant in comparison to the repair time. Okay, so when you see this, you'll see that this PFD or unavailability associated with I have had a dangerous failure, I detected it, but I'm going to continue to run the plant and not perform my shutdown or not perform a shutdown. I'm going to leave the safety function unavailable until I can repair it. So that's the unavailability between when the failure occurs and when you can repair it. Okay, the next term down is our online testing term. And right now I have it unchecked. I'm not doing any online testing. But what if I did want to do some online testing? So I'm going to say, yes, I'm going to do online testing. And then I need to put in, well, how long is this device in bypass to perform the test over the entire proof test interval? So if it takes me 1 hour to test these pressure transmitters, and I only do it once over the 48-month proof test interval, I'll leave 1 hour. But if I test it for 1 hour every year for 4 years, then it would be 4 hours. So what's the total amount of time for a test interval, an overall test interval, that you'll be in bypass to do an online test? Okay.
Okay, Ed,
so I
Ed, we got a question in the chat here.
Sure. Give it to me.
It says the diagnostic interval on this specific 2 out of 3 function, is it considering the entire SIF or 1 out of 3 PT unavailability?
It's considering the okay, that's a very good question, and I'll delve into this a little bit more when I actually show the equations. But the assumption that we're making here with the diagnostic interval, I'm sorry, can you say that again? Was it the diagnostic interval or was it the online test duration?
Diagnostic interval.
Okay, the diagnostic interval is for a specific component. It's not the SIF as a whole, it is a component. And not only is it a component, it is how fast are the automatic diagnostics on that component performed. So if you have a level transmitter, it's running its program, like a smart transmitter, will run its program about once every 100 milliseconds to every 300 milliseconds. And so once every 300 milliseconds, it's going to run all of its diagnostic routines. So you need to basically understand for each component, how are the diagnostics being performed and how frequently are they being performed? And that is going to be at the component level. Okay, the test duration is a little bit different. So the test duration, we're also looking at an individual component, but what we're looking at for the test duration, the assumption we're making, you'll see here that I have a 2 out of 3 vote. But I am making the pessimistic assumption that when I perform the test, all 3 transmitters in that 2 out of 3 vote are in bypass. Normally, you would not do that. You would basically do 1 transmitter at a time, leaving 2 transmitters in service. And at that point in time, you can actually argue that there's no unprotected online testing and you could kind of ignore the term. But if you want to be super conservative, you mentally make the assumption that all 3 of those transmitters are in bypass for the entire duration of the test. It just makes it the math easier. And you'll see, looking at the size of the term, not super relevant in terms of your total contribution unless your testing takes a long time. Okay, so in this case, over the course of a 48-month full proof test, I'm going to spend 4 hours in bypass, and that's going to give me a PFD of 1.1 E-4. So that's that online testing term, or the bypass duration term, goes by number of names. Generally, you know, in the original version of the report, we assumed that nobody's going to do this back in 2002 when that technical report was first released. Okay, the last term is that imperfect testing term. So that imperfect testing term says, well, I did a test, but my test wasn't that good. It wasn't perfect. So I didn't catch 100% of the failures. And so if you uncheck it, that means you assume that there's no contribution and that all of your testing is always perfect. 100% of failures will be detected. But when you click imperfect testing, the first thing you need to say is, well, how good is it? So let's say 99% because I'm doing a full functional test. I'm testing every known dangerous failure mode. I'm testing for every failure mode when I perform my online test, but I'm going to have some sort of allowance to say, well, maybe there's something that I don't know about that I couldn't test for. The other term you need to put in here, we call it useful life. Some people will call it mission time or mission. Basically, what we want in this cell is how long do you expect this device to be in service? So for instance, for a pressure transmitter, you could say, well, an electronic device is going to be in service for about 30 years before I pull it out and replace it, or 25 years. If you're doing something like a valve, you'll put in kind of a rebuild service. So like, let's say once every 5 to 10 years, I'm going to take that valve out of the process, take it back to the shop, send it back to the manufacturer, completely disassemble it, replace all the wearable components, lap all the services, and put it back in. And at that point in time, you're assuming that it's good as new. That good as new term basically resets the clock that says, if I'm good as new, my probability of having a failure is 0. So that's only going to happen once every 25 years. And even if I'm testing the device once a year, once every 2 years, once every 5 years, there's a portion of the dangerous undetected failure rate that's going to continue to accumulate over the entire life of the device. That term is what gets calculated here. So it's a function of how good is the testing, and how long am I going to allow that potential dangerous undetected failure rate to accumulate? So as you see here, in Vertigo, and I assume pretty much everyone else's software is going to work the same way, but it's going to be more expensive and not as easy to use. But I'm not going to get into a commercial right now. I'm going to go ahead and show you where these equations came from, because they all came essentially from the same place. So let me cancel out of here. I'm going to go back into the ISA training really quick. Okay, so if I go back a slide, and let me put this back up on full screen, you'll see that in this slide in the training, we're basically taking all of the failures that are possible in a safety instrumented system and breaking them up into different types. So some of the failures are safe, meaning they're going to result in a spurious trip. Some of the failures are dangerous, which means, as opposed to spurious, which means the plant shut down when I didn't want to or need to shut it down because nothing bad was happening. A dangerous failure, or a failure on demand, is something that if I challenge the safety function, it's not going to work. So an example of a dangerous failure mode, a good example of a dangerous failure mode, is a valve that's been stuck in place by corrosion. So when I demand that the valve go closed, it's not going to go closed because it's corroded in place and it's not going to move. So those are dangerous failures. But we take the dangerous failures and we're going to break them up into different chunks. And then those different chunks are going to go into the different components of the equation. So the DD term, those are the ones that I can detect with diagnostics. So if I have a transmitter that's communicating with the SIS and I get an open circuit because I dropped the wire, well, it could be a dangerous failure. It's definitely detectable because my signal went from 12 milliamps to 0, and it should never go to 0. So that's an example of a failure that I can detect. And because I can detect it, I can program the PLC to do something about it, like de-energize all the outputs and bring you to a safe state. There are dangerous undetected. So the DU term means I have a dangerous failure. So it's a failure that's going to prevent the safety function from being able to do its job. But at the same time, I can't detect that failure with diagnostics. The only way that I'm going to be able to detect that that failure is present is to do a full functional test. So if it's not detected by diagnostics, but it is detected by the full functional test, that's lambda DU. Lambda DN, the last guy, is those, again, those failures that are never detected by any type of diagnostics because the test is not good enough to be able to detect them. And then this slide will then kind of build out what those different failure rates are and how they're kind of, you start with a total failure rate and you start breaking things into smaller sections that you're going to shove into the different terms of the equation. Okay, so now where did these equations come from and what do they actually mean? So I'm going to now jump out of the, bear with me for a second. Let me close this out. And I'm going to go into the ISA training. The ISA training on SIL verification is available to anyone who wants to take it. It's part of our Process Safety Training Center. It's a self-paced training course. Technically, it's not done, but I digress. It will be done shortly. All right. So here are the equations, and I'm not going to go into full screen mode yet because I'm going to jump around. But these are the equations that are pretty much exactly the same as the equations that you see in the ISA EC50 training class. And for the 1 out of 1 voting arrangement. So there's the DU term, the DD term. the online testing term, the never detected term, and then the common cause term. So all those, we use different variables and they should match. And if you want a little bit more detail on that, Kenexis has an SIS engineering handbook. I think it's still available on Amazon, but if you're ever in Texas, when I'm in Texas, stop by the Kenexis Houston office. We got a big pile of them. I'll just hand you one. Okay, so, and again, these terms, the next slide kind of shows you in the Vertigo software where all of these terms are used. But where did these equations come from? So I'm going to give you the brief, quick and dirty version because I don't want to spend an infinite amount of time on where these equations came from. But if that's something you want to see, let me go back into my web browser, and I'm going to go to YouTube. So look at that handsome man in the green shirt there. Oh wait, yeah, that's me. Hair's not quite as gray, and I'm sporting the beard now because it's Movember. But I derived every equation that's used in the Kenexis Vertigo software, which is essentially the same as the equations that are used in the ISA training class, and pretty much everybody else's software should be using them. Don't get me started on the Markov model stuff. A Markov model, I'll suffice it like this to say that the equations that you're looking at are analytical solution equations, and a Markov model is only a numerical approximation. So why would you use a numerical approximation when you can use an analytical solution? Marketing is the answer. I digress. This video, so SIL verification equation derivation, it's available on YouTube. It is a full 48 minutes, so almost an hour of me explaining where these equations came from if you're really interested in knowing every last nook and cranny about where the equations come from, why they're valid, and why it's okay to use them. But now let me go back into the training class, and I'm going to go back a little bit to give you some fundamental, and I need to go way back in the training class to talk about reliability engineering. So where did the equations come from? They came from two essential concepts of reliability engineering, and they are unreliability, which is the complement of reliability, and unavailability, which is the complement of availability. Both of these terms are used in the SIL verification equations. The unreliability is used for DU, it's used for DN. Unavailability is going to be used for DD and the online testing term, and actually the common cause term is actually also an unreliability. So you're going to be using both concepts depending on what term you're looking at, and essentially whether or not it is a repairable system. So detected failures are a repairable term. So you're unavailable while you're performing the testing. So can you detect the failure while the plant's online and running is going to determine what form you use. So what are these terms? And again, I'm not going to give you the full level of detail that you would get in the training class. But reliability, term number one, is the probability a device will properly function over a given time interval. And this is the equation for reliability that you will never see because we simplify the heck out of it in order to get to where we need to go. All right, so reliability. Let me give you the light bulb in the closet example. And I don't know exactly where we are. So over here to the left off of the screen is a closet, and I have a box of light bulbs in front of me. If I want to know the reliability of the light bulb, This is the kind of test I would perform. I will take a light bulb out of the package. I will put it into the slot in the closet and I'll turn the light on. Then I will close the door and I will forget about it. I will come back 1 year later, open the door, and determine whether or not the light bulb is still lit. So I turn the light bulb on, and a year later, I'm going to come back and see, is it on, yes or no? The probability that the light bulb is still lit is the reliability. The probability that it is not lit is the complement, which is unreliability. So 1 minus R is unreliability. And that's kind of again, that full formal equation that you'll never use. So that's the term that we use for DU, DN, and common cause failures. Why do we use unreliability? Because in the middle of the mission, so from the time you put the plant into service to when you shut it down for a turnaround, that's your mission. In the middle of the mission, you will not know that that device has failed. The door is shut. So the only way that you will know that that failure has occurred is when you test it at the end of the mission, or if you challenged it and it didn't work and you had an incident at your plant because the safety function didn't operate. So unreliability is undetected failures, things that we don't know about, we don't see. The other term that we use, and I'm not going to belabor this, but there are approximations that we're going to use that are going to make our math simple. So the reason you never see an E in your SIL verification calculations is because we turned it into a line by using the rare event approximation. Okay, now if I can detect and repair in the middle of a mission because I have diagnostics. So when you have diagnostics, it allows you in the middle of the mission to be able to detect and repair a component. Now I have a different framework, a different mentality. I'm going to use a whole bunch of different terms that all have mean in them because I'm kind of using averages over time. And now for those failures that I can detect and repair mid-mission, I'm going to use a different concept. It is an availability. So if I go back to my light bulb in the closet example, when I did reliability, I took that light bulb, I plugged it in, I turned the light on, and I closed the door, didn't look at it, came back a year later to see if it was working. For availability, it's different because we're going to watch it the whole time. So for availability, I'm going to open my closet door. I'm going to put the light bulb in, turn the light on, and then instead of shutting the door and coming back a year later, for the entire year, I'm just going to sit here and I'm going to watch that light bulb. And I'm going to watch the light bulb and I'm going to watch the light bulb. And if at any point in time the light bulb fails, I'm going to immediately pick the light bulb, broken light bulb out, take a fresh light bulb, put it in, and the light gets turned back on again. So in the middle of the mission, I was able to detect and repair that failure. So the availability of this type of system is basically going to be the uptime, which is what fraction of the time was the light bulb actually lit, divided by the total time. So you see, reliability and availability are completely different concepts, whereas where reliability, you're kind of looking at a mission. What's the probability I'm going to be able to get through the mission without breaking? And availability, though, considers diagnostics, considers your ability to detect the failure, considers your ability to repair that failure, and how long it takes to do that repair. So uptime and total time is the actual real definition, but we're going to start using some acronyms and some other terminology. So for uptime, we're going to say that's the mean time to failure. So how long was that device in operation before it failed? And let me back up to this slide to kind of go into it in a little bit more detail. So this TTF, if we average them over a long period, That's your mean time to failure. So we're running, and then the failure occurs and we drop down to the failed state. And we're going to be in the failed state until we repair it. And this is going to be a term that I'm going to call MTTR, mean time to restore. I'll come back to some of the tricky terminology here in just a second. And then once you restore it, now we're back in an operational state. So your total time is this entire cycle that includes the mean time to fail and also the mean time to restore. So that's why the total time is MTTF times MTTR. So that's your definition for availability. But now we're pessimists in the SIS world. We don't care how well it works. We care how often it fails. So we're concerned with unavailability. And unavailability is given the letter Q because U is already taken for unreliability. So if you're wondering why your fault tree software like Arbor from Kenexis gives you an unavailability as a Q, the answer is U was already taken by unreliability. So unavailability is not going to be uptime over total time. It's going to be downtime. How long were you in an unavailable state? That's, again, the mean time to restore divided by the total time, which is mean time to restore plus mean time to fail. It is also the complement of availability. And that's how you calculate it. Now, even though this is the full equation, when you see the equations built out in the EC50 class or wherever, you're never going to see this form of the equation because you can't do integrals. If you're adding in the denominator, that just makes your math really difficult. So we are going to simplify it, and the derivation video explains how to do this simplification. But the unavailability is approximately the failure rate multiplied by the mean time to repair, and that's based on the assumption that the mean time to repair is going to be very small in comparison to the mean time to failure, which I hope would generally be true. That's rare event approximation number 2. All right, so those are the key concepts that the equations are based on. Again, the PFD is going to be a function of unreliability, and it's going to be a function of unavailability based on different terms. And I'm not going to give you the full training class because we only have, an hour and a half here together. You could go into a lot more detail and so there's our PFD average term and this is going to be used again for DD, DN, and common cause failures because those are the ones we can't detect and repair mid-mission. And I'm not going to show you all the calculus behind how you needed to calculate that. But again, in the video where I derive it, I actually do the calculus to show you that it's real. Unavailability is already an average. Okay, so now let's go into our multi-component systems. And before we go into multi-component systems, I'm going to talk a little bit about probability math. For most of you, this is a review of something you learned in elementary school, but it bears a little bit of discussion. So probability is the possibility that an event will occur. We're assuming that all of our events are independent of each other, and we don't need to worry about complementary events, but not mutually exclusive events. So too much detail here for our discussion today. But at the end of the day, for probability multiplication, you're essentially adding things together. And this is actually the more accurate term that actually shows you you're not actually multiplying things together, especially if they can happen at the same time, because they're not mutually exclusive. Okay, So this is the equation that most people are going to use in their calculations. You are just going to add your probabilities together if you have a logical OR. So the probability that a valve will fail or a switch will fail, you just add their individual probabilities together, and that's usually close enough. This little bit on the end that says, well, they could both be in the failed state at the same time, is generally negligible at the very low probabilities that we're using when we're doing SIL verification calculations. Okay, so that is probability addition. There's also probability multiplication for ANDs, and you can do your probability math for AND gates where you multiply or gates where you add. You can apply them to frequencies and also to probabilities under certain sets. So that's kind of a little bit of a precursor, little review of stuff that you already know. Then, the whole concept of SIL verification is a subset of a larger topic called fault propagation models. So in the reliability engineering, where we said unavailability and unreliability, we were simply looking at one component. But if I have a system that is built of multiple components, let's say a sensor, a logic solver, and a final element, I need some sort of mechanism to be able to combine those probabilities. That's a fault propagation model. There are tons of them. Fault tree analysis like Kenexis Arbor, Markov models, which are really great for SIS logic solver vendors with very complex repair schemes. But for you, the end user, the only time you would need to use a Markov model is if you want to impress your friends with stupid human tricks. But you're not going to need it to do SIL verification calculations. You generally are going to stick to your analytical solution equations and your fault trees. Reliability block diagrams work like fault trees, but hey, in the SIS business, we care about failures, not success. So fault trees over reliability block diagrams. So let me skip over kind of those concepts. I'm also going to skip over a little bit failure modes and effects analysis. Again, I explained earlier how you need to take your overall failure rate and split it into its individual components. And that you're going to do with failure modes and effects. Failure modes, effects, and diagnostics analysis to tell you and kind of split up which failures are safe, which failures are dangerous, and of those failures, which can you detect and which can you not detect. So kind of that might be another interesting webinar to have, is the failure modes, effects, and diagnostics analysis. Put that on the list, Chris. FMEDA. We'll do a webinar on that too. Good stuff. Okay, thing that I want to delve into a little bit more deeply right now when we're talking about failure rates is imperfect testing, because I already showed you ISA training class slides, the ISA technical report, Kenexis Vertigo, and any reputable SIS PFD calculation software tool is going to consider imperfect testing. But a lot of people, especially when they're first introduced to the concept of SIS, struggle with, what do you mean I tested the device and it worked, but you're telling me it's still failed? That doesn't make any sense to me. And the reason is there are some failure modes that you might not be able to detect depending on how you do your tests. Okay, so here is a great example of why we consider never detected failures. Let's say I have a pressure vessel. So here is my pressure vessel. It's got a flange on the outlet. It's got a flange on the top. And we also have a flange. We'll put the blind flange on here for a manway. Okay, here's our vessel. and we need to measure the level. And the people who designed our plant said, well, let me do this on the cheap. So what they did was they took a level transmitter, LT, and they're using, actually, sorry about that. Let me erase. And I want to actually make this an LSH. So level switch high. Okay, level switch high. All right. So for the level switch, it's kind of a float type level switch. So here is my float. And basically that float is going to move up and down on the shaft with the level of material in the tank. And if the level goes too high, the switch is going to activate and cause a shutdown. What could possibly go wrong? Okay, so now when I want to test this device, how do I do it? How do you perform a test of this device? Well, some people might say, well, let's just keep filling this vessel until it reaches the trip point. Whoa. Actually, testing an SIS by generating an actual real live demand on your process is kind of crazy. People don't do that, and generally they're going to want to test this during the turnaround. So how do you do this kind of test during a turnaround? So let me remove my level, and after I remove my level, now my float is sitting down here at the bottom. All right, so the tank is empty, my float's hanging out down there. How do I test this level switch to make sure it's working? Oh, I've got a great idea. I'm going to go out to the field. So I'm going to remove the blind flange on the manway. And I'm going to walk out. So this is me. I've got my hard hat and safety glasses, so everything's cool. I'll be perfectly safe. And what I'm going to do is I am going to manipulate. Actually, I kind of drew this poorly. Let me draw it so that it'll actually work. So I'm going to manipulate my precisely calibrated 2x4, and I'm going to stick that into the manway, and I'm going to lift that float up until it reaches the trip point. And when it does, the level switch activates and everything's good. Perfect test, yes? No, this is a very crappy test. So why is this a very crappy test? Well, what if? So when you're writing your test plans, you need to think about what are all the failure modes? What are all the different ways that this device can fail? So one of the failure modes that I know for sure exists with a float is a hole. So if there's a hole in this float, when the vessel fills up with liquid, the liquid is going to go into the float, fill it up, and it will never float. That is a dangerous failure for sure, because it's going to, in a high level trip situation, it's going to prevent this device from doing its job. Not only does this test I just showed you not detect that that failure mode has occurred, it can actually cause that failure mode to happen. I stuck my 2x4 in, I poked a hole in the float, and I went through the test and said it's working, but my test actually caused the device to fail. All right, so we're all, or a lot of us are instrumentation and control engineers. What should we be doing? Well, we should have installed a level bridle. So I'm going to have some flanges to the process. I'm going to connect a bridle here. I'm going to have valves that are going to allow me to bleed off pressure on the top. I'm going to be able to bleed off liquid on the bottom. Actually, I kind of drew that poorly because I actually, let me do that. I'm actually going to want my level transmitter. So it would be better if I had my level switch on this external bridle, because then if I want to test it, I can simply isolate from the process, drain the liquid out, and then put liquid in the top and fill it up to the trip point and make sure that it activates. So if I were to do this method over here, this is infinitely better, much more testable, much more maintainable. A direct level measurement inside the vessel, you're just asking for trouble. So you might say that the calibrated 2x4 method of testing the level switch will have like maybe a 50 to 60% chance of being able to detect a failure, because a lot of the known failure modes it can't detect. Whereas this approach might have closer to a 95% diagnostic coverage, because if you have that hole in the float, you'll be able to test for it. So hopefully this example kind of impresses upon you why we're doing all this extra math to look at never detected failures, because they are realistic and they're really going to put the brakes on the effectiveness that you think you're actually getting out of your safety instrumented function. Okay, so that's imperfect testing. Let me get back into the equations a little bit. FMEDA. I talked about failure modes. Bear with me for a second. All right, so now we get into the voting arrangements. So everything that I showed you on the ISA slide was for a 1 out of 1 arrangement. And what do we mean by 1 out of 1? So 1 out of 1 means I have one device and that device needs to vote to perform a shutdown. So it's a single switch or a single valve as part of a safety instrumented function. And you know that for 1 out of 1 voting, you have no fault tolerance to dangerous failures. You have no fault tolerance to safe failures. If the device fails dangerously, you're in the failed state. If it fails spuriously, you're going to have spurious trip. And when we're doing these types of comparisons, I just threw some numbers up as a starting point to where we can compare the different voting arrangements. Now we're back to where we started in this training class of all of the terms. So the DU term, when you look at the DU term, what you have here is it's effectively lambda T over 2. This is our unavailability. I'm sorry. Somebody needs to catch me. Unreliability. Dangerous undetected failures exist for the entire mission. You cannot detect and repair a DU failure mid-mission. Therefore, the appropriate way to model it is unreliability, which is lambda T over 2 is the average unreliability over the mission time. It's not the lowest, it's not the highest, it's the average. The DD term. So actually, before I hit the DD term, again, DU is an unreliability, and DU is the term that you will always evaluate. Every other term, you can give a rationale for why you didn't evaluate it. But the DU term, you will always evaluate. There's never a reason not to evaluate it. It's always present. So always.
All right.
The next term is
question here.
Yes.
Is the proof test coverage set as 99% by default in Vertigo, or is it extract by the specific item type selected from the database?
Okay, there is no default diagnostic coverage. manual proof test coverage. So when you uncheck the term for imperfect testing, it's going to give you blank slots for proof test coverage and for mission time or useful life of the device. Now, we don't give any recommendations on what that imperfect proof test coverage is, because in order to know that, you have to know how it's being tested. So it's inappropriate to have an imperfect or a manual proof test coverage in a database, because it depends on how you test it. So now, if you go and look at data from some equipment vendors, Emerson does a really good job of this. They will give you a menu that says, if you test it like this, this is your proof test coverage. But if you test it like this, this is your proof test coverage. And if you test it like this, this is your proof test coverage. So it's not an attribute of the device that you could just stick in a database. It's an attribute of the device and the procedure that you use to perform the test. So we don't include that in our database of equipment items, because it's not a function of the equipment item. It's a function of the item and how you test it. So it's not something that's going to pop up automatically. It's something that you're going to need to enter in. Good question, though. Okay. All right. So the DU term, always there. The DD term is not always there. So there are two reasons that you're going to need to use the DD term. The number one reason, I'll just start drawing here, is diagnostics. So diagnostics are those high speed, high frequency automatic tests that the equipment performs on itself. Not all SIS equipment has diagnostics. So if there are no diagnostics, DD is going to equal 0. The DD term goes away because there are no diagnostics. So you're only going to evaluate the DD term if you have diagnostics, and a lot of times you don't. The second reason that you're going to evaluate the DD term is if you have the diagnostics, and if those diagnostics tell you that your device has failed, what do you do? And the answer is continue to operate with failure. So the DD term means I did a test, I know the device isn't going to work, but I'm going to continue running the plant anyway. And I'm going to basically assume that I can send a technician out there to repair the device before it gets challenged. Now, there are other clauses in the standard that are going to require to use other compensating measures to replace the failed component with a human being or something else in that time period. But mathematically speaking, we're assuming that for the time duration it takes to repair that device, the safety function is not going to work. Now, if you check the box that says trip on detected failure, you're not going to evaluate the lambda DD term. Why are you not going to evaluate the lambda DD term? Because you're never unavailable. If you detect a dangerous failure, you shut your plant down. You're never unavailable while the plant is running. So only if you have diagnostics and only if you continue to operate the plant, you don't shut down when that dangerous failure detection occurs. So for that time duration, you're unavailable. So we're going to use U was correct here. Now we're going to use a Q. This term is an unavailability, and the simplified equation for unavailability was lambda times the mean time to repair. Whoa, lambda, MTTR, mean time to restore. So that term is a unavailability. So basically, it's what is the probability that it's going to be working, given that I can detect that it's failed and I can repair it mid-mission. Now, the mean time to restore is a little bit complicated because it includes two parts. The first part is the MRT. MRT in IEC 61511 is the mean repair time. So how long does it take to actually fix the device? That's the first part. And if you say, remember when I was showing you Vertigo, I typed in a 0. When I typed in a 0, I said that this second half is insignificant. So the mean time to restore includes the amount of time that it actually takes to perform the repair, but it also includes the automatic diagnostic test interval over 2. What does that mean? Well, there's a certain amount of time that elapses between when the failure occurs and when you know that the failure is present. And that is going to be a function of how often you do the test. So on average, you will be in the failed state for half the time that it takes you to know that the failure has occurred, or half the time that it takes to perform a test. So if you test a device once a week, then if the device is failed, on average, you will have been in the failed state for 3.5 days before you knew that that failure occurred. So automatic diagnostic test interval over 2. So that automatic diagnostic test interval, again, for high-speed diagnostics, transmitters, logic solvers, that's happening in the millisecond range. When you add 300 milliseconds to 48 hours or 72 hours to repair, you still have 48 hours or 72 hours to repair. So essentially just ignore it, zero it out. But if you're doing a partial stroke test that takes a long time, a week, a month, a quarter, now it becomes relevant. Okay, so the DU term, unavailability associated with a failure I know is present, but it's going to take me a certain amount of time to fix that failure. And during that time frame, I'm continuing to operate. Okay, next term is the online testing term. It is, again, a Q. Oh, I already wrote these down. It's a Q. It's an unavailability. So if you look at it, you have the test duration divided by the entire mission time of the safety function, which is the manual proof test interval. So what duration am I bypassed for testing over an entire 5 or 6 year or 4-year test interval that I would use for the safety function as a whole? This is an unavailability, but now instead of this simplified lambda MTTR, you're really doing downtime over total time. So the time that you perform the test, you're down. Your safety function isn't going to work. And you divide that by the total time, and you're going to get an unavailability. So what fraction of the time was the light bulb not lit? You know, it's downtime over total time. That's where that term comes from. The DN term, which now I've spent a lot of time explaining that DN is real. It's something you need to think about. But again, it is an unreliability. So we're using, again, lambda T over 2. The lambda is the DN, but it's a failure rate times test interval over 2. And the reason we're using this is never detected failures aren't detectable. Sounds kind of simple to say. In order to use an unavailability, you have to be able to detect and repair online. DN are never detected, and technically they're never repaired either. So the whole concept of unavailability makes no sense. It's an unreliability. Now, common cause term I will get to when I show you the 2 out of 2 voting arrangement real quick. So once again, this is where all of these things go. in the Vertigo SIS software. So we have our DU term, we have our common cause term, we have our DD term, which if we say trip on detected failure, it's going to shove that number out as a spurious trip. But if we uncheck, it's going to then take that and calculate the DD term. So depending on whether or not you shut down when you have a detected failure determines what side of the ledger you assign that failure rate to. We have our online testing term. We have our imperfect testing term. You add all of them together because it's a logical OR. My device can fail DU or DD or never did ND or online testing or common cause. Because it's or, you add everything together to get the total. So, all right. Now, I'm going to spend a couple minutes here talking about a very subtle concept. And the ISA training kind of gets away from this by kind of ignoring this SD concept. And it's why the equations that you see in Vertigo are going to be slightly different from what you see in the EC50 and 52 and 54 training classes, because the EC50 class kind of simplifies the concept a little bit and just basically says, I don't care whether it's SD or SU, all of my failures are safe. They're all going to result in a spurious trip. But that's not actually true, because you can have a safe failure that you detect and you can choose not to shut down on a safe failure if you can detect it. So that's kind of a bizarre concept. What you're looking at here, those of you that are aficionados of SIL verification calculations can see that I've drawn you a Markov model where I have my state 0 is an okay state, and this is for a 1 out of 1 device. I can fail to a safe detected state. I can fail to a safe undetected state, a dangerous detected, and a dangerous undetected. Now, you'll see that dangerous detected is always red. It's always dangerous. I'm always unavailable. Your safe undetected means you're going to do a spurious trip. It's always going to be a nuisance shutdown. It's always going to be a spurious trip. It will never be a dangerous state. But the diagnostics, you'll see that I drew these as half red and half green because it might be an unavailability. It might be a spurious trip, depending on how you configure your shutdown system. So when you have a dangerous detected failure, and I'm going to use the colloquialism, a detected failure is a bad PV. Bad process variable. That's kind of common terminology in DCSs. So if I have a bad PV, what do? If you continue to operate, you have made that bad PV dangerous and an unavailability. If you shut down, you made that bad PV a spurious trip. So for my dangerous detected failure, I can convert that failure to be safe by programming the PLC to trip, or I can configure it to be dangerous by setting up an alarm for maintenance and continuing to operate the plant. The other lesser thought about concept is you're doing exactly the same darn thing with safe failures. So if a safe failure is detected on a transmitter, there's a very good chance that you can convert that safe detected failure into a dangerous failure by not shutting down the plant, by throwing up the alarm and telling maintenance to go fix it. So in Kenexis software, in Vertigo, we don't assume all safe failures are going to result in a spurious trip. We basically take all of the detected failures. So all detected, whether it's safe or dangerous, and then we take that total pot of detected failures and call it a spurious trip if you vote to trip or call it a DD unavailability if you choose not to trip. So we've acknowledged the fact that you can actually take safe detected failures and convert them into an unavailability, into a PFD, if that's what you program your PLC to do, because your PLC knows it's a bad PV. It doesn't know, well, if it's a bad PV on the low end of the scale, it's safe, but if it's a bad PV on the high end of the scale, it's dangerous. It just knows it's a bad PV, which is why we treat all detected failures, whether they're safe or dangerous, the same way. And you'll see that in our equation sets when you see how the software works. Okay, so the next term is the spurious trip rate calculations. I'm not going to dwell on. We kind of do roughly the same thing. Break it into its components, add the components together to get the overall spurious trip rate. Okay, so let me kind of close out by just going over the other architecture. So 1 out of 2 voting means I have 2 devices. If one of them says to trip, I'm going to trip. 2 switches in series, 2 valves in parallel, give you a 1 out of 2 vote. You have 1 degree of tolerance to dangerous failures, no tolerance to safe failures. And this is going to be your equation set. So where do these terms come from? Look at the YouTube video if you really want to know, but basically we're doing probability math on the equations. So effectively, a 1 out of 2 vote is a 1 out of 1 equation and a 1 out of 1 equation. So you're effectively doing probability multiplication. But as you'll see, that's a 3 out of 4. So it's a lot more complicated than just adding or using the probability math. But more on that is going to be in that YouTube video if you wanted to watch it, which there you go. There's another shot of that YouTube video for those of you that are hardcore. 2 out of 2 voting is our, where 1 out of 1 was safety, 2 out of 2 is spurious trip avoidance, which is going to give you 1 degree of tolerance to spurious trips, no tolerance to safe failures or to dangerous failures, even more dangerous than a 1 out of 1. And there are your equations for 2 out of 2. 2 out of 3 is kind of weird. I can't really describe it because it's basically 3 2 out of 2s or 3 2 out of 2s or 3 1 out of 2s, depending on whether you're looking at safe or dangerous. But the interesting thing about 2 out of 3 voting, it doesn't give you 2 degrees of fault tolerance to anything, but it gives you 1 degree of tolerance to dangerous failures and 1 degree of tolerance to safe failures. And those are your equations. So when you use your equations for all the individual components, then you're going to use your probability addition because you have an OR to add the PFD of the sensors, logic solvers, and final elements to get your overall PFD. Your risk reduction factor, as everyone knows, is 1 over the PFD, and that's where that number came from. So all of that is kind of summarized and simplified when you go into Vertigo and you start looking at a component. Let's bring up the valves this time, which is in a 1 out of 2 voting arrangement. So that's where all of this stuff came from. And now on the valves, you see it's not nearly as interesting because we only evaluated the DU term. Actually, I take that back. We should have evaluated. I've been doing too many demos. We should have evaluated the beta factor because we're doing a 1 out of 2 term. But no diagnostics, no online testing, no imperfect testing. So we're simply adding those 2 terms together. All right. So with that, that is that's basically it. That's the big picture. I went almost exactly an hour and a half, which is what I was shooting for. So now let me go ahead and leave this up And I didn't get a whole lot of questions during the meat of the seminar today, and I'll just go ahead and turn the floor open for any questions that anyone might have. Chris, can you tell me if there's anything in the chat?
Yeah, there's a new one here. It says, is there a K out of N SIF degradation, a calculation box whether is D or S?
Is there a degradation? So the ability to, all right, so let's look at a 2 out of 3 voting arrangement. For a 2 out of 3 voting arrangement, when you detect that the first component has failed, you can program the device to change the voting arrangement to either now be a 1 out of 2 or a 2 out of 2. So a bad PV, you could throw out the bad component and now revert to a 2 out of 2 vote or a 1 out of 2 vote. We don't do that. That level of detail really is never going to show up in your significant digits. But so what we do in Vertigo is the truest form of the equation or of the voting arrangement. So in 2 out of 3 voting, when a device fails, we assume that that bad PV generates a vote to trip. So if I have 3 devices, one of them is in the vote to trip because it's in the failed state, the remaining 2 are effectively a 1 out of 2 vote. So that's how we're basically assuming if your component is in the failed state, it will either be a vote to trip or not a vote to trip based on what this flag says, vote to trip or not vote to trip. So we're not doing any more advanced, okay, switch it to 2 out of 2 here, and if you get 2 degradations, switch it to 1 out of 1. We don't do that, that type of kind of advanced degradation, because that type of advanced degradation, although we could do it, the PFD associated with the PFD change associated with that advanced degradation is going to be many significant digits irrelevant. So if your PFD is 1.01 E minus 2, if you did that kind of analysis, it would be 1.01000002. So it's not really relevant. So basically, we're doing a true. It's either your bad PV is either a vote to trip or it's a vote not to trip, and that determines whether your degradation goes to a 1 out of 2 or a 2 out of 2, or then a 1 out of 1. Hopefully that answered the question.
How do you calculate the fact that the same SIF is used for several LOPs in the HAZOP?
Okay. It doesn't change anything. Okay, all right, let me explain. Okay, so everything that we've been talking about, it calculates the PFD for the safety function in isolation. It is an independent, isolated subset. Stochastic is a term that some of the reliability geeks would want to use, meaning that it doesn't depend on anything before, it doesn't depend on anything after, it doesn't depend on anything coincidental. Completely independent, isolated system. That's what we calculated the PFD of. Now, this safety function is going to be considered or part of scenarios that you're going to run a layer of protection analysis on. You're usually going to run your layer of protection analysis way before you did your SIL verification calculation. For a greenfield plan, at least, let's say. Now, every LOPA scenario contains an initiating event. Initiating events are discrete, infinitely short points in time. So each LOPA scenario is a trigger and then the activation or failure to act one or more independent protection layers. Every initiating event for every LOPA scenario is completely stochastic, it's completely independent, it's completely isolated. The fact that a safety or an IPL, whether it's a safety instrumented function or not, is used in multiple scenarios does not change the frequency of any individual LOPA scenario, because all of those LOPA scenarios are independent of each other because they begin with an initiating event, which is an infinitely small point in time. So like, and this kind of also goes back to the concept of double jeopardy in a HAZOP. And it's because we're assuming that lightning can strike the same spot 2 different times, but we're assuming that the probability, the concept that 2 bolts of lightning will strike the same spot at the same time is so ridiculously infinitesimally small, we're not going to consider it in our math. So because your LOPA scenario begins with a frequency, which is a simultaneous, infinitely small time duration event, they are all independent of each other, and therefore you're not considering a cumulative effect that this independent protection layer is used in multiple places. That just LOPA doesn't consider that for that reason, and that's ultimately the long and short of it is every LOPA scenario is independent, and the fact that you use the same safeguard in multiple LOPA scenarios doesn't change anything about how you do your PFD calc, and it doesn't change anything about how you do your LOPA.
Okay, Ed, comment here says, but when you have 10 initiating events, the chance that something happens is 10 times higher than a single event.
Well, absolutely. So wow, we're getting a little bit off track into LOPA, but so for every LOPA scenario, okay, let's say we have a LOPA scenario with multiple initiating events. The mathematics in your LOPA, it can vary depending on what your company's preferences are, but what we at Kenexis espouse and is truest to the mathematics is a LOPA scenario will be caused by multiple initiating events. And the frequency of the scenario is calculated for each initiating event independently. So initiating event 1 is going to result in accident event 1. Initiating event 2 results in accident event 2. And so for each initiating event, you multiply the initiating event frequency by the probability of failure of all the protection layers. You do that for each initiating event, and then you add all of them together. But even though you're adding all the initiating events together to get a total frequency at which the accident event will occur, each one of those initiating events was independent of each other. So even though you're using the same IPL for initiating event 1 and initiating event 2, those initiating events are independent points in time. You're not requiring your IPL to address both initiating events simultaneously because they can't happen simultaneously. So yes, you add the frequencies of the initiating events together, but each row in that calculation is independent from each other row, even though they might contain the same safeguards.
Matthew, I see you have your hand up. Do you have a question?
Yeah. No, actually, it was a bit also for clarification, I suppose, of the question of Serge. Hi, Edward, by the way.
Matthew.
No, is one of the point you got it because we typically do cause driven PHA and then LOPA. So of course it's not the consequence driven. So of course we have a swap on that, and probably the other clarification would be as well when you have different scenarios with different risk reduction factor requirement, how Vertigo is taking the max out of those. I think that's done automatically when synchronizing with Vertigo, if I'm not mistaken, but up to you to correct me on that.
All right, Matthew, that's very interesting. That's a very interesting question. A lot of operating companies, and I'm gonna probably back up into OpenPHA again to talk about this. But a lot of operating companies have chosen and set up their risk tolerance criteria to do kind of a more traditional LOPA, which is one cause, one consequence is my scenario. I'm not going to look at multiple causes of the same scenario. And basically, if I have multiple scenarios that are all using the same safety instrumented function, then I'm going to pick whichever one is highest. Okay, so how does that happen? All right, let me back up a little bit. I've been in the details of the SIL verification calculation, but let me go back to the IPF list and let me hope that I have the synchronization correct, which I might not. So when you look at the IPF list, so this is a list of all the safety instrumented functions, and you go to SIL verification summary, you see this item here called link to LOPA, and I don't have all of them linked. So when you see this link to LOPA, I can press a button to add a link to an OpenPHA study. I can delete the connection, or I can synchronize the connection. So when I synchronize the connection, what it does is it's going to bring up the information on the left that I see in the OpenPHA study, and on the right, what I see in the Vertigo study. So I can synchronize things. Now, when I say sync IPF, I can, and I did this just for an example because these aren't even the same safety functions. You're able to change the Vertigo study to match what's in the OpenPHA, but you can never change what's in OpenPHA because that would be a violation of every PSM rule to allow a PHA study to be changed without a full team agreeing to what the change is. So we're not going to let the SIS engineer click a button and change what's in the PHA. Now, you'll see that this safety function is connected to an IPF. It's connected to a independent protection layer in Vertigo. So let's go into Vertigo and see what those look like. I'm sorry, let's go into OpenPHA and see what those look like. So if I go into OpenPHA, and I've done way too many demos on this, so there's a bunch of junk, but if I click on safeguards and pick one of the ones that should be connected. So UZC 101A, this is the one that I should have been connected to. You see that this interlock, so the Vertigo study connects to this record, which is the interlock. This interlock needs to have a certain PFD. It needs to have a certain SIL target. This interlock needs to have a certain PFD. It needs to have a certain SIL target. And this interlock, though, can show up in multiple scenarios. And I'm going to have to well, you can see it here. It's not as clear, but you'll see that this interlock shows up in 3 different scenarios. So if I show the LOPA worksheet, this interlock shows up in this LOPA scenario. It shows up in this scenario. Well, these are all different scenarios for the same, or I'm sorry, different initiating events for the same scenario. But as you Matthew know, that you can use a same safeguard in multiple different scenarios. So this one actually is in different scenarios. So fire detection system. Where's my fire detection system? It didn't show it to me. Sorry about that. But again, if a safeguard is used in multiple different scenarios, all of those different scenarios will show up in this list. But the safeguard itself isn't going to have multiple SIL targets. You can only assign it one SIL target, and that SIL target needs to allow you to achieve tolerable risk for all of the LOPA scenarios that it might show up in. So here I've got 3 initiating events. Here I've got 2 completely different scenarios that this safeguard shows up as. But you define the performance, the required performance of that safeguard once, and that's what the scenario is linked to. So if I go back out of OpenPHA, go back into Vertigo, let me actually try to link that LOPA scenario where it should be linked. So I'll go into here, and it should have been linked to this guy. Oh, and return to Vertigo. Okay, so now, no, it didn't do it. My gosh, I have to delete the linkage first. But you get the point. The point is there is a target. There is a safety function that resides in OpenPHA. That safety function has performance targets associated with it, and it can show up for multiple initiating events and multiple scenarios, but there's only one target, and it is that safeguard that's linked to Vertigo, not the scenario. So the IPL is linked, not the scenario. If you want to see how that safeguard is used in the multiple scenarios, then you need to jump out of Vertigo and view the link in OpenPHA directly. You need to see where it shows up. That answer the question?
Yeah, no, for me, yes, it was, I think, more an explanation for Serge, or where to link, or how to see the multi-tool recall of a function.
Yeah.
But I actually want to come back on the degradation question
Yes.
I made there. So I understand that from a point of view of PFD calculation is not included. My question was more, is there any way within the Vertigo calculation where I can see what would be the PFD achieved when degraded towards safety or reliability, so that it shows up that if I mean, what would be in case of degradation the achievement?
Okay. So that's not something that we're doing right now. So let's say that for this 2 out of 3 vote, if I could click a button to say that it's degraded, meaning one of the devices is in the failed state, what PFD is it achieving now? Yeah. No, that's not something that we have right now. It's something that we need to think about, not necessarily here in Vertigo, but in the Bowtie tool, where we're going to be more concerned about kind of showing you an online, what is the current status of the function. So everything that we're looking at here is we're in design mode. So everything is working, everything, this is the PFD before, the average PFD. What we're not showing here right now is real-time PFD and degraded status PFD, which are more of those things that are more relevant to operations as opposed to design. But, you know, I'm just going to walk 10 feet away and tell Sean to put that on his to-do list.
And
just a remark on this one. If you have a 2 out of 3 and you automatically goes to a 1 out of 2 when you detect it, you can just change this voting from 2 out of 3 to 1 out of 3 to 1 out of 2, and it should be more safe as well.
That's a very good point. It would actually, that degradation would make it safer. Oddly enough, but you know, many of you, I'm sure, are experts just as much as I in this topic. So yeah, degrading to 1 out of 2 would actually improve your PFD achievement. But if you degraded to 2 out of 2, that would wreck it. And yeah, you could put that in, but it still would be very interesting, I think, for a lot of people to, when they come to this sheet for an operating plant, instead of seeing the PFD as designed, to see it right now, instantaneous PFD right now. We could put another column down here.
It was just to not denature the original configuration. That's why
right.
I know that if I change the 1 out of 2 voting, I can get the result immediately. It was just to not change the nature. As you said, this is, now we are speaking about operation. Of course, as end user, we are in operation, so we think much more in operation and not the, sometimes design like it is set up, as you said, right now. So take it as an operational comment, food for thoughts and things like that.
No, absolutely. And in terms of, you know, management of change, it would be nice to kind of let people know, if I put this device in bypass, what does that actually mean? Where am I at?
Yeah, because that would be the consequence of this question will be, what am I using that status for? Because you have the possibility to put it in bypass by putting the status select item to bypass. But then I would expect then a triggering, but bypass what? The entire function, or you have like a sort of degradation, and then so things like that, you know?
All right, well, consider it on the upgrade list. I will let Sean know as soon as we're done here.
But yeah, and just a bit of clarification also on the answer you gave me about the trip on detected failure. So the diagnostic interval I need to put there, is it for the single item of a 2 out of 3 logic, or it's for the entire SIF? Because I don't see the difference. I mean, at least here in the calculation, I don't see the difference whether I am in a like 2 out of 3. I have one of the item which is detected failure, but I do not stop the plant, and then I go into degradation mode. So what should I put there?
No, the time to detect is for a single component.
Okay.
Now, if you're, and this all goes back into the equations and how the equations are derived. So the trip on detected failure, if it's a 1 out of 1 vote, then it's a very easy to calculate unavailability. Or unavailability if you don't vote to trip. But if it's a 2 out of 2 vote, we also have the logic that says, okay, well, this is the probability that one of the devices is in the failed state, but both of them have to be in the failed state. So that's accounted for in the equation, that both of them have to be in the failed state before a failure occurs. So for a 2 out of 2 vote, a second failure would have to occur.
So if it is a 2 out of 3, is looking, of course, at the out for tolerance, then it takes the reason why it should be failure as a SIF, as okay.
Yeah, so it's this number is for one component, and the fact that you have redundancy, all of that is in the terms of the calculation.
Yeah. No, because I was surprised that for this figure, let's say configuration, I put like 1 year, so 8,760 hours, and it was like a 10 to the minus 5. So I say, wow, I was not
Right.
expecting being so nice, but
Well, actually, you know, this is really, really interesting because the way that you're doing this, you're let's see here. I'm mentally trying to remember how the math goes, but basically, you have reverted to a 1 out of 2 vote. So even though one of the 3 transmitters takes a year to get fixed, you still have a 1 out of 2 vote of the other 2 transmitters.
and 10 to the minus 4 if you go to 2 years. So, but I did a bit of test on this specific item you had there on the screen because I was curious while you were talking about this parameter.
Yep. Absolutely. Fun with numbers.
Yeah, exactly.
All right, Chris, is there anything else before I turn everyone loose to get back to their day jobs?
No, I don't see anything else at this point.
All right. Well, thanks for everyone for attending. It's been almost 2 hours. I appreciate everyone's time and everyone's attention. Also, I've got, I think I had you list out 3 new topics I want to give webinars for. So that's going to be more good stuff coming up in the future. So keep your eyes on our website and the newsletter for the next things that are coming up. Thanks everybody for your time and attention. I appreciate it. Chris, you go ahead and wrap us up.
Yep. Thanks for the excellent presentation, Ed. As Ed mentioned, we're going to get this recorded webinar out on our website. We'll let you know with a post on our website and on LinkedIn as well. So again, consider following Kenexis on LinkedIn. And with that, we'll end today's webinar. Thank you, everyone.
Thanks, everyone. Have a good day.